And so with that, I'll kind of kick it off here. So yes, I'm Tim Knauer with Fluence, and I've been there for the last 3.5 years on the commercial ag sector side. So the crops I'm dealing with are predominantly high wire, leafy greens, as well as strawberries. And one of my first projects with Fluence was actually looking at the interaction of pollinators with LED lighting and sort of how that played out. So this has been a topic of interest for me for actually quite some time here. And how this is going to be sort of broken up is I'm going to show or talk about the generalities of insect interaction with light, and then our professionals or experts at BioBest are going to dive a little deeper into details with questions and things like that. And so what I've done here is I've separated these into two different categories. So we're going to talk about pollinators first and then pest and beneficials, because there aren't major differences, but there are some differences there as how they interact with light. And so within these categories, we're really going to talk about how they see or interact with the light, what the lighting factors are when dealing with them, as well as what the growing factors are, because you don't ever really want to separate the lighting factors and the growing factors because they play together in the environment. So we're going to start with pollinators, and really the main pollinator that we're looking at are bumblebees. I added honeybees in here as well because you do see them used in some strawberry crops. And so, but predominantly what we're dealing with is for bumblebees. So how do these pollinators see? Well, they have trichromatic vision. So they're really focused in on the UV, blue, and green receptors. And so they don't actually utilize the red or far red light. And so this plays a big role in spectral signaling because flower pigments have certain spectral properties, as well as the radiation source on the flower gives it a certain spectral quality. So it's important to know what your radiation source is for that reason. So this is really how pollinators are viewing the light. And so let's kind of look at what the lighting factors are then, if that's the case, when you have pollinators in your grove. So one of the main lighting factors is photoperiod. And with pollinators, photoperiod doesn't actually have a direct effect on their foraging habits as long as the intensity of the light and the spectrum of the light is optimal. So really what we mean here is bees will forage properly under long day or short day conditions, as long as your intensity of light is high enough to wake them up properly and to really keep their activity going throughout the daytime period that you want them to be active. And so bees forage highest under these middle of day conditions. So really what we consider like high natural light conditions in the middle of the day. And so in winter months, you really want to replicate that in order to get the proper activity out of those pollinators as well. And they're most important. So kind of one of the things to focus on here is spectrum, because they're most efficient at foraging under full spectrum light because they can spot and identify the flowers best, which plays into the spectral qualities of those flowers and then the illumination source on the flowers. It's good to note here as well, UV light range is used for orientation and navigation. So when looking at your greenhouse, pay attention to the UV filters and coverings you have on that, because even though they don't take a ton of UV light in order to navigate properly, they can be disrupted if the coverings are too heavy, or if you have very low natural light conditions, say in wintertime, and you still have these UV coverings on the greenhouse, it can disrupt their kind of orientation process as far as foraging goes. So kind of continuing with that, spectrum does play a role in this, especially in the wintertime. So with narrowband spectrum lights, they're not sufficient for that proper activity in the low natural light condition times because of that high red content that we talked about, where they're not really utilizing the red light, and then the lack of the middle wavelengths that are really needed to stimulate that activity. HPS lights we can't ignore either because they're in a lot of grows. And so just some things to keep in mind with HPS lights is they do give off a strobe effect because they run on AC voltage versus DC. And so this can have a negative effect on your bee's ability to navigate because they perceive images much faster. So to them, that strobe effect is heightened essentially. Also, the HPS spectrum is heavy on the yellow to red spectrum side of things. And so it also is deficient a lot of times for bee activity in those low natural kind of winter conditions. Also, we can't ignore the fact that, well, we also all know that HPS lights get quite hot. And so when bees get too close or they accidentally hit them or bump up against them, it usually causes death to the bees just because of the excess heat. LED lights also can have a strobe effect, so I don't want to kind of blow past that. But that's only if they're being run at less than 100%. So say if you have LED lights currently and you have them dimmed down quite a bit, they can also have a strobe effect. So just keep that in mind. So moving on to the growing factors with pollinators specifically, one of the things we see talked about a lot is, CO2 enrichment, because it's a part of most of our crops because we're pushing them to flower and to fruit. And so CO2 enrichment, all it's doing is actually increasing, as far as pollinators are concerned, it's increasing the nectar and pollen production, and can make flowers actually more attractive to bees, which just increases the pollination activity. So it's a good thing. CO2 enrichment at levels of say 1,000 ppm or less, which are pretty typical, you usually see that 500 to 1,000 ppm range, have been proven to have no negative effect on bee activity. So this is all good news. Temperature does play a role as well in optimizing your pollination because bees are cold-blooded. So your optimal greenhouse air temperature for getting the most efficient use out of them, especially bumblebees, is that 68 to 80 degree Fahrenheit range or 20 to 27 Celsius. And so that's a pretty big range, and that's usually the optimal temperature for most crops that we're growing are within that range anyways. So as long as you're maintaining that, temperature should not be the limiting factor with your pollinators. And to sort of sum all that up, the optimal environment for bee foraging specifically is under full spectrum, medium to high intensity lighting with warm temperatures and a CO2 enriched environment. So now that we've kind of breezed through pollinators, we're going to break this down a little more with your pests and beneficials. So these are the crops we chose to focus on: tomato, cucumber, pepper, and strawberry. And then we've put essentially the pests on the left side here, and then the beneficials you would use to treat them on the right. I'm not going to go through each of these individually, but the main pests we've sort of targeted are spider mites, thrips, whiteflies, and aphids, because they seem to be basically the top pests that you're dealing with these crops. So the pests and beneficials as well, they seem very similar to pollinators as far as I know. So there's no major differences there. So they're going to be focusing in on that UV to yellow range. And then UV and blue are used for navigation and orientation predominantly. Also, as well as pollinators, you have to make sure they have enough of these certain wavelengths needed for navigation. So when we talk about UV, if you have heavy UV filters, having blue light maybe in your spectrum of light can also help alleviate that issue, but just make a note of it when looking at your greenhouse. Lighting factors that kind of feed into this, overall, providing a higher light environment will only increase the activity of these listed pests and beneficials. So as long as your temperatures and your food sources aren't limiting for your beneficials, just having a higher light environment is always beneficial. So with increased lighting, though, the benefits balance out between your pests and beneficials. So because I get questions all the time, well, if I'm making a good environment for my beneficials, is that just going to basically increase the pest population? Well, no, because they balance each other out. Overall, yes, a lot of times you are going to see that they need very similar environments. So just keep that in mind. But if they're both healthy, they will end up balancing each other out, and it works. So another thing to note here is also the photo period, because photo period, I remember I mentioned, wasn't as big of an influencer with pollinators. It can be more of an influencer with your beneficials, because some beneficials actually require a minimum photo period for this proper activity. A good example of this is really Aureus, because it requires a minimum of a 12-hour photo period. And so before, if you did not have artificial or supplemental lighting in your greenhouse during the winter months, you couldn't use aureus to treat thrips. And so now you can actually, if you have artificial lighting, you can use aureus all 12 months in order to treat all your thrips. So that's just another advantage of supplemental lighting in general. Spectrum is going to be exactly the same as with pollinators, because those narrow band spectrum lights are not sufficient in these low natural light conditions of winter because of that higher red content. Because either way, insects really aren't utilizing the red at all. So it's important to focus in on spectrum for that reason. Also HPS, you can go through that as well with your beneficials, because the lighting does give off an excessive amount of heat. Now this can kill flying insects, beneficials, but also this excessive heat, especially in your high wire crops, like tomatoes, it lowers the humidity in the top of the canopy, which can negatively affect some beneficial activity compared with, say, LED lighting. So a great example of this is Persimolis in order to treat spider mites. So your Persimolis actually suffers under high heat and low humidity conditions, so below that 65% humidity range. And thus it will actually move to lower parts of the canopy in order to get into a better environment. Spider mites, on the other hand, actually perform well in these conditions. So they'll stay at the top of the plant where it's high heat, low humidity, whereas the Persimolis will move lower into the canopy in order to find a more ideal environment. So unfortunately, even though you're treating with Persimolis, it's not being effective because they're not actually interacting with each other because of that light source that you have affecting your environmentals. And Persimolis are, can be quite expensive, so you want them to be functioning at their best as possible if you're using them. And so a good alternative to Persimolis in this case, if you have HPS, is actually Californicus, because it's better suited for that dry, hot condition. So this just kind of plays into make sure you know what your lighting source is, make sure you know what your environmentals are throughout the canopy, not just, a daily average, and really keep track of what your grow is like so that you're getting the best use out of those beneficials. And so this really does depend on the species of insect and where the life cycle occurs. So this is when you would be working with your experts at, say, BioBest, and figuring that out for your crop. But also it's important to monitor these things throughout your grow in order to know what these numbers are. Just a couple other things to mention with lighting on pest beneficials is lights can be used as traps for pests, especially the Lepidopteran pests. That's something we see just from a homeowner standpoint, but it can also be applied to grows. HPS lights, as we talked about before, they can attract and kill beneficials like they do pollinators, because aureus and other flying parasitoids would be up in that range where the lights are and hitting them. Another really important point for greenhouse growers is also when the lights are on at night or evening in the greenhouse, you can attract pests into the greenhouse from outside. So that being said, pay attention to when you're lighting outside of those natural daylight hours, and make sure your vents are closed during those time periods so that you're not essentially inviting more pests from outside fields or wherever into your greenhouse kind of unawares. And so just when you're lighting, make sure to monitor exactly if your vents are open or closed, and kind of work through that. It just helps prevent new pest populations from moving in. And then you need full spectrum lighting for scouting as well, because scouting is one of the most important parts of anyone's IPM strategy. So what we've noticed is when you start playing around with spectrums of lights, especially in low light conditions, if you have heavy red blue type spectrums, monitoring your crop can be quite difficult because it actually changes the color of the leaves and whatnot. So it's hard to see damage from pests, and it's also hard to just see properly underneath them. So it's something to keep in mind for just your overall IPM strategy. Now that we've talked about sort of the lighting aspects of beneficials, we're going to dive a little more into the growing factors. So temperature as it played a pretty big role with pollinators, it also plays a very big role with beneficials because they can affect the activity and the life cycle speed of a lot of these insects. So I'm just going to leave it to there because we can dive deeper into that in the questions as well. But just know that temperature obviously does play a big role in these. And so you need to know what beneficials you're using, what's their optimal temperature, and also then base it off what your crop optimal temperature is and see what works. A good example of this is 2 common whitefly beneficials that were studied under differing conditions. And this was in a tomato greenhouse with supplemental light. And so what they noticed was Incarcia, which has been used widely in winter because of its low temperature range tolerance, actually wasn't performing as well as Aretinoceras, which previously wasn't used as much, but it actually does work well under these same conditions because it can actually parasitize and it can host feed. And so it was actually getting much better treatment of these pests because of those reasons. And so now instead of just using Incarcia to treat whitefly, they actually use a mix of the 2 species typically in winter now. And so this is just a good example of how temperature and lighting and everything play a role in what beneficials you're using. Also very good to note that food source consistency is more crucial for some beneficials versus others. So Aureus is a great example of this as well because it feeds on pollen, as do your bumblebees. And so if plant vigor and flowering is increased by, say, increased light or CO2 or both, this should increase their vigor overall as well. And so if you don't have this increased vigor on your plants, otherwise, if you don't have that, you actually need to provide the food source for your beneficials and your pollinators so that they'll be able to function at an efficient level or more efficient level, especially throughout these low food source time periods. And so really looking at the overview of what we've got here, lighting is just one component of your grow that affects insect activity. We know that. So make sure to dial in the ideal environment for your plants first, and then your pollinators and beneficials. When it comes to spectrum, narrow band spectrum lights are not sufficient for proper activity in low natural light conditions. I'm harping on that because it's really the winter conditions that make the big difference. Because they're focused in on that higher red content and they lack the middle wavelengths that are needed to stimulate that insect and pollinator activity in those winter conditions. And so one thing to note with pollinators especially is when lighting them, they do need to be locked in their hives when the light levels are too low or they will get lost. So if you're not using supplemental lighting, sometimes the natural light levels will not be high enough to really stimulate them to wake up and to get moving. If you are using supplemental lighting, then know when you're turning the lights on, then opening the hives, allowing the bees to wake up, and then basically do what they need to do throughout the day, bringing them back into the hive, closing the hive, and then shutting your lights off. So just know that order, and obviously that's something you can talk through with your insect expert as well that you'll be working with, whichever company you're using. But that's just another benefit of supplemental lighting, is that you can kind of control that aspect of when you're using your pollinators and sort of activity you're getting from your pollinators. Also beneficials, one note to look at here is higher rates may be required in the winter months due to that limited light and temperature, and thus you'll have limited insect activity. So that's just another benefit of using supplemental light in general, is that you can bolster that insect activity because you have more light, and hopefully you're able to maintain the correct temperatures because of the crop you're growing. And so having supplemental lighting allows your crop to grow more efficiently and bolster the flowering, but also it allows your insect activity to be optimized so that hopefully you're not required to buy as many beneficials as frequently. You'll get better use out of them. And then always good to note here, it's always a numbers game when looking at your pests and beneficials, because as I mentioned before, they tend to have that same or very similar ideal growing environment. So as growers we always want to look at what the plant needs first, obviously, because that's key. And then you want to look at what your beneficials and your pollinators need, and then determine the best solution for your grow. And so that obviously depends on what kind of crop you're growing, and then what the environmentals and lighting needs are for that crop. And so with that, I'm going to say thank you, because this is not an easy topic. It's not one that's had a ton of research done on it. And so we're always looking for collaboration with research departments, with universities, with growers, because even the research that has been done has been under legacy lighting. So usually HPS or very narrow band LED lighting. And so we really need more field research under full spectrum lighting to gain a better understanding of how insect behavior differs to truly find that best solution. And so thank you all for that. And I am going to now pass it on to Nikki for the start of the Q&A kind of section here.
All right, well, thank you so much, Tim. That was very informative. And to your point, certainly learned a lot in what seems to be a bit of an emerging issue. So I've got a couple questions here that popped up into the chat early on while I have you. Specifically clarifying, so there were some questions asking about the bees, whether it was Bombus or Mellifera, or if it's all diurnal bees, what your studies were done with regards to pollinators.
Gotcha. So just to preface this, Fluence has not done studies specifically. This is generalities from studies that have been done by universities and also insect companies. But I would say I'm actually going to let Simon answer that one, because he is actually the bee expert.
Right. Start video. How do we do this? Yeah. Okay. Well, so bees see within a very narrow spectrum of UV light between about 315 and 400 nanometers. This is not a wavelength that we see ourselves, but it is the same for both bumblebees and honeybees.
Okay, so to clarify then I'm guessing that the research you're speaking to would cover all bees, right? All diurnal bees?
Yes, indeed.
Awesome.
Indeed.
Okay, also the second question that we had here, there was another one that came quickly or early on in Tim's presentation about what are some of the negative effects that are seen above 1,000 parts per million of CO2?
Yeah, I saw that too. So CO2 is heavier than air, and it tends to sink. And so when you're pumping in CO2 into a growing facility, it will tend to drop. And I don't know, Nikki, whether you've ever held dry ice in your hands, but it falls. You know, the dry ice falls because CO2 is heavier than air, and it tends to collect lower down in the crop. What is natural CO2? 400 parts per million or something like that, 350. 1,000 parts per million, yes, it's high, but actually these organisms, what we mustn't forget is that these organisms can move, yeah? They can move and they can find places where they're comfortable, yeah? You know, if they find themselves in a situation where the CO2 is too high, they will move away from that.
Okay, so I imagine that it's going to reduce pollination or take them away from the areas that you're looking to have the bees located?
Well, of course, most flowers are higher up in the crop, and so the CO2 is going to be dropping down and doing its stuff with the foliage and the leaves lower down. So I don't see it as a problem, but I haven't studied this in detail, so I can't give a clear answer.
I think I should kind of preface that. So it wasn't that they necessarily had adverse effects at higher ppms of CO2. It was the fact that most of the studies were done with that 500,000 ppm range, because that's usually what growers are using. And so they just wanted to make sure that there was no adverse effects. And so there weren't. So using higher ppms of CO2 aren't necessarily going to have a damaging effect on the bees. It is, though, important to notice or to note what Simon said, because a lot of bee hives are actually stored underneath crops. They're not necessarily, it's not great for them. A lot of times you want them in the aisles and higher up, but the actual boxes themselves are stored pretty low. And so when you have the high CO2 levels and the CO2 sinks, the home of the bees is actually in a pretty high CO2 environment, whereas where they're foraging is not. So it's not necessarily causing an issue, but it's just be aware of it.
Yeah. And if you look at occupational levels of CO2, I think it's 800 parts per million for 8 hours. 1,000, ppm. It's not that high,
Okay. All right. So it looks like there might still be some more research that needs to be done in that area as well.
Oh, yeah.
Of course. And Nikki, I think, something to preface this whole thing with is there is so much we don't know.
Oh, of course. Well, that's always the sign of any good research, right? Is you answer one question and you ask 1,000 more.
Exactly.
All right. So I've got another one here too. It says, what is the best solution for pollination with bumblebees in fully LED growing rooms?
Okay, I'm curious. That sounds like they're talking about maybe sole source applications of light where like there's no natural light.
I got that impression as well.
Yeah.
There you go.
Okay.
Yep. There you go.
Yes.
Clarified.
Okay. Yeah. So that Simon, have you actually had any interaction with pollinators in sole source kind of applications? Because most of the time I don't deal with pollinators in sole source applications, because most of the crops that I'm dealing with that are grown in a sole source environment for lighting are going to be the leafy greens. There's not a lot of strawberries being grown in sole source. That's very new. There's not a lot of growers doing that. The high wire crops are not, they're not grown in sole source conditions most of the time because it's just too expensive. I know there's a lot of experimentation going out there right now with sole source lighting, but for me personally, I have actually never seen bees used in a sole source environment in a grow. So I can't really answer that. All that I would say is talking about full spectrum lighting in a low natural light condition in wintertime in a greenhouse, that definitely applies to sole source application, because a sole source application, you're providing all of the light. So it would definitely be beneficial to use a full spectrum light that is closer to the natural sunlight versus a narrow band spectrum light, because I'm sure you're going to get some of that narrow band light.
Yep. So there are two issues here. One is that bees don't see in the same way that we do. Bees see in this very narrow spectrum of UV light between 315 and 400 nanometers. They have a bit of visibility in the orange and that's one aspect of that. The point is, if they can't see, they can't perform. It's as simple as that. And bees, and the second point is, bees, when they leave a hive, and it's wonderful to watch, when they leave a hive, they pause and they look and they orientate themselves to a UV source. And that UV source that has evolved over many millennia is this big glowing thing in the sky called the sun. Yeah, and they orientate to that, and they fly around, and they can find their way back to their hive. So lots of research has been done to try and augment performance of bees by providing UV light and this sort of thing. But actually, I do a lot of work in Finland, in places like that, and in Finland they tend to grow under plastic, double skin plastic, where they pump hot air in between the two layers, and it's great. Keeps the place warm, but there is very little UV light coming in. Now, the bees don't perform very well. Okay, they, as I said, they have this small window of UV light that they can see, but then they also see a little bit of the orange light as well, and so they fly into Sonti HPS lights and stuff like that, and they burn themselves, and the hives last 2 or 3 weeks, and you know, it's a bit of a disaster. But actually, there are things that you can do to help them do that. You know, help them improve that. One is, these bees seem to learn to be able to tolerate lower levels of UV over time. Yeah. So, you know, we're talking Bombus terrestris, standard bees, and given time, they can learn to perform.
All right, awesome. All right, thank you so much for that. It was very, very helpful. I also want to add in another question here as well. I'm getting a couple of people sending them over my way. One of them was specifically asking about whiteflies, and it asked, why are whiteflies worse in winter cucumber crops with lights, and what can you do about it? Not sure who would be the best one to answer this one.
Yeah, Amanda. Yep.
Sure, I'll tackle that. You know, we're kind of speculating a little bit, but assuming that it is the effect that Tim mentioned of the HPS lights in winter reducing the humidity in the crop. So it's partly that the lower humidities make it more difficult for Incarcia and Rutmerceris to work really well. And of course, those parasitoids can also be attracted to the lights and die. And then there are a few other factors. So if you're lighting in those winter crops, you know, the pest responds to the increased light intensity and the radiant heat as well from the lights. And so the whiteflies do quite well under those conditions. So, you know, that's HPS. If we were talking about LED lights, you likely wouldn't have the drying factor and wouldn't have the radiant heat factor. But I haven't yet seen a lot of crops, winter cucumbers, for example, or tomatoes with LEDs yet. And then, you know, I also suspect that in the past, people relied quite heavily on Incarcia for winter whitefly control. And we've kind of learned that they can be less effective in those winter conditions. And so what you can do about it is, our recommendation is to rely a little bit more heavily on Swirsky, a predatory mite, and Nutrimite, which is a food source for the Swirsky, so cattail pollen. And I've seen that combination increase the Swirsky population by 10 times. So once you get, and it also, the Nutrimite, the food source, helps the Swirsky establish faster. So we're really then targeting the eggs of the whitefly. And what you'll see if you've got, a big whitefly population is that you've got a lot of eggs in the heads of the plants, but then they get taken out by the Swirsky and you end up with fewer larvae and then even fewer pupae. So, so that's it's a great strategy. That some numbers, we use 250 grams of Nutrimite per hectare per week, weekly, applied to cucumbers. And then another recommendation to really boost the numbers early, because there's a bit of a delay with the sachet release, is to do a few weeks, 2 or 3 weeks of Swirsky bulk releases at about 25 to 40 per meter squared over those new plants, just sprinkled. And then you're feeding them, and you get your Swirsky populations up really, really quickly. And then if you're going into the winter crop with a lot of adult whiteflies, maybe from the previous crop, a few weeks of high rates. So people don't like these high rates, but it's just a couple weeks of Eretmaceras at somewhere between 10 and 20 per meter squared really helps to bring the whitefly levels down so that you can get through the winter crop well. And so a lot of that also, just to kind of bridge between cucumbers and tomatoes, is relevant in tomatoes as well. Not the Swirsky part, but what Tim mentioned about the research by Gabriela Zilahi-Balog and Les Ship and others. They showed that, you know, under winter conditions of low light intensity, low temperature, and short day length, Eretmaceras wins over Encarsia because of higher levels of parasitism and also higher levels of host feeding. So using at least, you know, we don't recommend 100% Eretmaceras, but a mix of Eretmaceras and Encarsia, because there will always be little pockets and microclimates within the crop where one works better than the other. So yeah, and Encarsia, of course, you know, didn't perform as well one-to-one, one female to one female of Eretmaceras, but in reality, the Encarsia population is almost 100% female. So, you know, that can compensate a bit for the lower parasitism levels. So a mix rather than just the Encarsia is good in winter.
Yep.
Yeah.
And Amanda, if I can add to that, I wanted to talk about this concept of be the bug. You know, this whole concept of understanding the microclimate and what it is to be the bug. The number of times I've walked into a crop and the grower says to me, the temperature is 30 degrees, the humidity is 40%, all of my bugs must be dying. But actually, if you go into the canopy and you look at the underside of the leaf where these organisms are living, it is a completely different world, you know. And if there's one thing that I'd like to get across in this webinar is for people to actually be the bug and think about how these organisms exist and what their world is, because it's very different to ours. And when we're talking about Eretmaceras eremicus, before the taxonomists got their hands on it, it used to be called Eretmaceras californicus because it's from the deserts of California and Arizona, and it's very cold there at night, but it's very hot during the day. Now, these organisms don't operate in the dark. They don't operate in the hot day. They operate in the short period where there is high humidity, where the leaves are still cold, but the sun is coming up, and that's when they do their work. Yeah. So the whole concept of being the bug is understanding that these organisms, you know, that they're not just you know, kind of like machines that operate all day. They do their stuff when they need to do their stuff. Yeah.
Awesome. Thank you.
I didn't explain
yeah,
it very
no,
well.
I agree. The microclimate and yeah, I think that they're not robots. They have their specific requirements, and yeah.
Yep.
So I do want to change, I guess, the questions up a little bit. I know it was mostly done on insects, but we do have a question here wondering if there's any studies that have been done on lighting or spectrum studies with regards to mildew suppression.
I can mention that, or Tim, you can take it, whichever.
Yeah, I'll jump in here.
Okay,
So
yeah.
suppression has been, yes, there are experiments that have been done on it. This webinar specifically is about pollinators and insects, so I'm not going to dive deep into that. A lot of the mildew suppression has been using blue, heavy blue, or even UV light in order to kind of kill spores. But that's a whole nother ball game. Like, it's not related to the insect control. Yes, there's quite a bit of research actually. I would say there's a lot more research done on that than there is on the interaction with beneficials and pollinators.
Mm-hmm.
Yeah,
and I've started to see now, especially in strawberries, but yeah, the UV machines that go over the crop at night to kill mildew. So there, yeah.
It is good to mention though, because if you are using that UV light, that's at higher levels, like much higher levels than insects would need. It's actually damaging levels. So like people aren't allowed to be in the crop when they're doing this. So that can play into insect activity or even death. I don't know how that plays into that. Could possibly kill some beneficials.
Yeah, so to answer that, I think, and what you see in the activity on the mildew is that it really only affects the mildew that's exposed directly to the UV light, so that anything that is shaded by another leaf is not going to get killed. You'll get patches of white, where the UV can't reach. Yeah. And
it's not penetrating through the leaf.
It's
surface.
not getting through the leaf.
Yeah.
So the bugs are generally underneath the leaf. So I don't think it'll have a huge impact, but yeah, yep. I think research needs to look at that.
Yeah, it's kind of how it ties together. So it's you always need to make sure what you're doing isn't affecting other aspects of your growth.
Mm-hmm. All right. Well, thank you for that. And it sounds like we might need to have another webinar to look at some other aspects that are being done too, right?
Yes. So always more webinars to do.
Lovely, perfect. Thank you so much. So I've got one here for Simon, and it said that Simon spoke of the Finland experience. So growing in LED lit greenhouses is like using a sole source of light, like indoor growing chambers, because of the absence of sunlight for many months. So are bumblebees entirely ruled out, or are there special bumblebees developed to navigate under LED lighting?
No, there are not special bumblebees adapted to those conditions. It is just accepted that the hives don't last as long as we'd like them to.
Oh, okay.
And maybe just to add to the pollination under LED and zero natural light, there are some pollination robots coming out indoors with zero UV light where the bumblebees can't be effective, might be the perfect place for pollination robots to take that role. Mm-hmm.
Very cool. Mm-hmm. For sure. Also, I guess as a great follow-up to that question, what would you consider to be best practices for using bumblebee pollination in lit crops?
Well, I can probably answer this. I mean, as we've said before, Nikki, bumblebees see in a very kind of like tight part of the spectrum. A lot of growers are lighting from 1 a.m. to 5 p.m. Natural daylight is maybe available from sort of 7 in the morning till 5 in the afternoon. These are organisms that need UV light to see. Yeah. They have some ability to see red, orange light, which is like our HPS and things like that. But it messes with them, and they can't navigate with it, and they burn themselves on the lights. So best practice, certainly in Benelux, what we do is, okay, we light the crop from 1 in the morning, but we only open the hive at like 9 o'clock in the morning. Once the sun has risen, you know, even if it's behind clouds, there is UV light coming through. And then we close those hives at about 3 o'clock in the afternoon, in such a way that the bees can fly back into the hive but can't come out again. And it's really important to protect the bees. You know, they do super work, but you know, only in selected periods, and it's really important to protect them as well. And you know, you know, we need to use that daylight wisely. We need to make sure that houses are not UV blocking. We need to place the hives as high in the crop as possible, to make the best use of UV light. And you know, when you've only got 5 hours of daylight, you know, and an extra half hour of light is big. You know, it's mega. So essentially, to summarize, we need to protect the bees from the dangers of flying in low V periods.
And of course I mute myself. So obviously it sounds like it's a lot more complicated question than just here's a 1-minute answer and a solution, but we wouldn't all be here if it was that easy, right? So I'd also like to open the floor up if there's any other questions, if any other growers have some questions available, because that's the end of what I have here. Otherwise, I'm happy to let everyone get out free and enjoy 7 minutes of undirected time.
Well,
right.
well, Nikki, we didn't get to talk about diapause in Fiddleites and aureus and things like that. So, you know, maybe some comments about that. There are a lot of questions about Fiddleites, and Fiddleites is of course a midge. It's a sessidemyid midge, which lays eggs, has predatory larvae that pupate, and people often ask us, what is the point of using a Fiddleites when this is an organism that goes into diapause at less than 13 hours of daylight? And my answer to that is, we produce these things in 16 hours of daylight. So the organism that is released in the crop is a pupae, hatches into an adult, lays eggs. The eggs hatch into larvae, are voracious predators of aphids, and then diapause is induced, and maybe you don't get the next generation. Of course, there are a number of ways that you can kind of extend the day length to keep them out of diapause. For example, even incandescent bulbs can do that. They don't respond to red light, but incandescent bulbs. The other question we often get asked is aureus. Aureus insidiosus is a very important product in North America. Aureus undergoes a very different type of diapause. So Fiddleites, the aphid predator that we talked about, undergoes what's called facultative diapause, which essentially means that it doesn't have to diapause. I've reared a Fiddleites for years and years and years without it going into diapause. But aureus, on the other hand, goes into a thing called reproductive diapause, which essentially means that adult females don't lay eggs after becoming adults if they decide that the eggs that they're going to lay will hatch into babies that will have nothing to eat. And I think it's a really, really very sensible strategy for any reproductive organism. Now, it's the late instars of aureus that are particularly sensitive to this. The adults are also very sensitive. What is really interesting for us here when we're doing a webinar with BioBest and Fluence is that blue light can keep these things out of diapause. So low-level blue light, if you give an aureus 9 hours of natural daylight, it will go into diapause. But if you add 6 hours of blue light, then that beast will think that it's the middle of summer and it will carry on reproducing. So there is this whole kind of, now that we're looking in more detail about how we light these crops and what wavelengths are best for growing plants, I really think there is a massive arena for studying what is going to help the beneficial insects to perform best.
And can I just add one thing as well? I'm sure many of you are aware, but there is a lot of research starting to happen on lighting and different spectrums. And it seems to be very pest and species specific, basically. Different wavelengths, different temperatures, different conditions affect different species differently. And so there's some really high quality work happening right in your backyard at Ag Canada and Omafra. And there's some really fantastic presentations and papers online by Sarah Jandrusik, Rose LaVey, Les Ship, and a lot of others that I don't know as well. But yeah, so look up those names and you'll find a lot of detail, species-specific detail on spectrum and different pests and beneficials.
And Amanda, I think it's fair to add that we at BioBest are looking at this in detail and with gusto.
Mm-hmm. Yeah, it's a fascinating area.
Yeah.
Absolutely. All right. Thank you so much. And thank you so much, Simon, for touching on that, just with some of the different predators and biologicals we use there. But here we are at the end. Didn't get any additional questions, so I guess you got one last second if you have one that's burning that you need to ask. Otherwise, feel free to connect with myself offline. Otherwise, I'd like to thank Amanda, Simon, and Tim for their great presentations and discussion points and answering a lot more questions than we're used to having. So thank you very much. And as well, you guys will, all of our grower members here at OGVG will be getting another update for the next Fluence webinar, which is actually going to be taking place in September. And it's actually going to be focusing specifically on IESO rebates and how to access those. So we'll stay tuned for that. But thank you very much. And I hope everyone has a great afternoon. Take care.
Nikki,
yes.
Can I just say one more thing?
Of course.
Be the bug.
And with that, I'll leave you all to your afternoon, and I hope you have a great day. Take care.
Thank you, everybody. Bye-bye.
Thanks.